Hey everyone, welcome to this first masterclass on PDG. Now, PDG is a technology that we recently released with Houdini 17.5 and also comes as its own application, Pilot PDG. It is a fairly deep technology, so that even with a masterclass, we can't cover all the aspects of it. But we have to start somewhere, so here's the first one that talks about some basic concepts around PDG. We'll cover topics like the key constructs in PDG, that is the processors, partitioners, and mappers. We'll talk a little bit about how to customize PDG for your own needs, such as being able to kind of add your own kinds of processors to the system. A little bit on the schedulers, just the basics. That is a custom binding of schedulers is its own topic that deserves its own masterclass. And we'll end with a couple of tips. Okay, so without further ado, let's get going. First, let's actually look at the key constructs in PDG. As you can see here, there are three of them. Actually, in the entirety of the 17.5 launch video, there was actually only two types of constructs were being used in that entire hour-ish presentation. So those only involved processors and partitioners. It didn't get to the mappers at all, but we'll talk a little bit about it today. So the point here is that despite the fact that there's all these nodes, it seems in PDG, there's this really simple underlying architecture behind it. And once you grasp it, you'll see how kind of PDG works. Okay, so a processor, you can think of it as simply some kind of a function. It's a thing that knows how to do something. Okay, so practically anything can be a processor. So for example, an HDA processor is just something that knows how to run an HDA. FFmpeg processor knows how to, invoke FFmpeg to make videos. ImageMagick can manipulate images. CL.exe, for example, is a compiler that knows how to take C files and turn them into compiled object files. So any of those can be a processor. It can be a pure function. It can be an executable that can be run to produce some output. And in fact, processors doesn't even have to involve computers. It can involve humans. An animator is a processor, can be a processor who takes in as input a rig and produces as his or her output keyframes. So it's a very, very broad definition. Processors take WorkItem. Okay, so WorkItem is one of these dots here. It's essentially the invocation of a processor. So if you can think of a processor as a function, then each of these dots is an invocation of that function, is a call to that function. And so a work item is just basically a little bundle of data. It has some arbitrary attributes on it. It may or may not end up spawning a task. Okay, and if it does spawn a task, then it would also hold on to the results of these finished tasks. So with that said, let's just take a quick look first at how this might work. So here I'm going to put down a top network. So we can see that a little bit better. Okay, so inside the top network, I'll put down my first processor, maybe a generator, and we're just going to up it a little bit. Say 3, right click, cook it, and there we go. We'll have 3 work items. Okay. Now you'll notice the generic generator doesn't actually do anything. There's a field here for the command, but I haven't filled it out, so it'll just cook instantly. If I middle mouse on these things, you can see it has this idea of an index. It has a priority. If I attach a kind of attribute create thing to this, we can get these work items to have some more attributes. So for example, here, I'll just call this foo_int or something like that. Give it a value, like say, I don't know, 5, and cook that. And these cook instantly, and now we'll have some attribute on it. That is 5. Both of these are examples of processors that don't do anything. These don't do anything, but obviously we can, when we plunk down things like, let's say, Rob Mantra. Here it is, Rob Mantra render. That would kick off actually a Mantra render, so that would actually do something with those tasks. Or an HDA processor, for example. Right, and you point it to an HDA, and it will spawn off Houdini engine to run that HDA. So these would actually do something. When they actually finish doing their thing, though, they will have a result. Okay, and the work item would hold that result. The simplest way for us to illustrate that is with a file pattern node. So, for example, then if I put down this file pattern here, and I simply run it. And by default, it goes to PDG dir, which is where our file is, where we saved it. And you can see it picked up two files. There's this PDF file that's there, and then there's the file we just saved. Okay, but you can see that the output is the quote unquote bake result in this case of the file pattern node, which is the files it found on disk, right? So any kind of when something actually runs, it has some kind of a bake result or something like that. It does show up on the work item as well. So you can see that having a single processor is kind of like having a parallel for each. So if I put down an HDA processor here, I can point it to some HDA file. If I were to up the number of iterations, I can get it to run that HDA files, in this case 3 times, all of it in parallel. That's great, but a single parallel for each is not yet that interesting. So what we'll want to do is really stack these processors together to allow for fan out, as you can see here. So if I were to put down a bunch of generic generators, we can see this effect. So if I set the iteration count to 3, I cook it, I got 3 things. And if I hook 2 of those together with exactly the same settings, and for each one of those 3, it'll spawn 3 more. And if I were to do that again, it'll just kind of keep on going and fanning out. So this is interesting. Obviously, we'll want to be able to fan that back in. And in a moment, we'll talk about kind of partitioners, and that's how we do that. But before I do, I want to talk a little bit more about when the spawning actually happens. This can happen one of 2 ways. These work items could either spawn before anything cooks, or it can spawn based on the upstream bake results of upstream work items. So in the first case, being able to spawn before anything cooks is what we call the static case. In other words, you kind of know everything ahead of time so that you can describe what your graph really looks like ahead of time. Okay, and that's what we call a static graph. Versus the second case, where you can only spawn these downstream work items based on some attribute bake results that was created during the actual computation of a work item. In the launch, you might have remembered that we showed a scene where we moved this bridge and moved this road. Depending on how we moved that road, how far the road was off the ground, we either spawned a bridge or we did not. Okay, so that would be a dynamic case, because we need the bake result of the road to see how far it's off the ground to determine whether we have a bridge work item or we do not. Okay, so I'm gonna put down a Python processor node. And here you're gonna see a couple of tabs, but the default one is this tab called generate, and it says on generate callback. Okay, so this is the really important one, because all work items in PDG basically come into existence through this on generate callback. And here on the side here, you'll notice a little tab that has actually a bunch of little code samples. I always like these because less memorization to do. And so we'll pick this one, the evaluate spirit parameters one. And here you can see looking for a spirit parameter called iter count. It gets the count from that, tries to figure out what the custom attribute, you type custom attribute in here, and it will set it as a stream parameter. So this is pretty much what we actually want to do. So we're going to do exactly that. Just going to add a few lines in front just to say this was called. So print on generate called and what its parents are. Okay, so parents and print upstream underscore items. When I dropped in this little bit of snippet here, some of the original comments disappeared. So I'm just going to show you what the original comment looked like. So you can see here, upstream items is one of those things that's already predefined. And so I can use it. Okay, so I'm going to get rid of that and get back to the one I was working on. Okay, so we still don't have the iter count and custom attrib parameters. So let's go add that. So edit parameter interface. And one of them is an int. So let's see here, float integer, and let's just throw that over somewhere, just before the processor tab, I suppose. And we'll call this iter count, and this integer, and let's apply that. So that shows up. And then we wanted something just called custom attrib, right? And that was a string. So let's go find that. Here's my string parameter. And just drop it in the same place. Okay, so call this custom attrib and trib string and apply that. There we go. So they both show up. Accept. So let's say we generate 3 work items here and create a custom stream attribute just called foo string. Okay. And now if I cook this, that should show up. And in fact, bring up the console here on generate called, we see that we have no parents at all. Okay, so let's clear that. I'm going to dirty this node. And here under tasks, if we say generate static work items, this will cause the first pass of the graph to be invoked. Okay, so you can see here the onGenerate called gets invoked, and our work items get added into the system. Okay, so to back up a little bit, there's 2 passes to the evaluation of PDG. This first pass, which gets called when you say generate static work items. This is the pre-cooking pass. And during this pre-cooking pass, onGenerate gets called, and we can see that we've added the 3 work items here. Okay, now to make things a little more interesting, let's add another one of these Python processors. And this time, what we'll do is we will clone the upstream work items. You can see here it just goes through the upstream items, and it says add work item, but to clone the result data. Okay, and just so we can see what's happening, I'm gonna just kind of copy these 2 lines here, paste it, and onGenerate in clone gets called, and then print the upstream items. Okay, and then we'll hook these together, set the display flag, and let's see how this is going to work. So dirty all, and I will clear this. Okay, and now if we go generate static work items, you'll see that each of the 3 gets generated again, and that's reflected here. Generate gets this first part of the call. And then the onGenerate in the clone also gets called. But what's interesting is that notice all 3 upstream work items were passed together to the onGenerate method, right? So it gets all available upstream information in order to do its work. And you can see the dependency relationships are already actually set between these things already. They're just not cooked. Now when I go right-click and cook selected node, this will now actually do the work, if any, that's associated with these work items. And that would kick off the second pass of the PDG compute, right? So the first pass being the onGenerate being called when we say generate static work items. And then as a second pass, it actually goes and computes these things. That's the second pass compute. This is actually a good time to bring up the issue of the API for PDG, because we're using some of that here. I just clicked on the help for the Python processor node. Now, what you need to do to see the PDG docs is just in the search here, say PDG, just search for that. And you can see that comes up in the user guide. If I click on PDG, there we go. Okay, so you can see the PDG package. And here is all the classes and methods inside of PDG. Okay, I was calling some stuff on the work item, for example. So here is PDG work item, and you can see the various methods here. So that covers the two passes of compute, right? So you get one pass when you say generate static work items, and then you get another pass when you actually go and cook it. If you just go and cook it without explicitly saying generate static work items, it will go and do that anyway, okay? Okay, so to fully contrast a static graph versus a dynamic one, let's take a look. So this one here is what we call the static graph, right? It's every single work item here was able to be generated during this first pass, the generate static work items pass. And you can see that while they're not cooked, all the dependency relationships between them are already set. And we have actually a description of everything that's ever going to happen in the system. So this is a static graph. It's advantageous in the sense that because we know everything that's about to happen, we can take this entire description and hand it off to the farm scheduler, and it can go and work on all these things for us and give us very accurate kind of ETAs because we know everything that's ever going to happen in advance. This is in contrast to a dynamic graph where, let's say if we dirty everything here, and I set the second Python processor, it was actually originally set to automatic. When it's on automatic like this, it will automatically guess whether it should be static or dynamic based on what the settings above. And because this guy is set to static, the first one here would guess static. Okay, the second one will end up being that as well. But in this case, we're going to explicitly set it to dynamic. And now, if I clear this, if I say generate static work items, you'll notice that only the first one generated those 3 work items. And the work items in the second Python processor does not exist at all until these things actually end up cooking. And based on its bake results, such as the elevated road, for example, it would have to analyze the bake results to see whether it needs to generate work items, and if so, how many. The work item generation will not happen until the graph actually cooks. So when we actually go and cook this node, you will see the onGenerate callback for this node being invoked. Okay, so there it is. And in fact, notice that it's a bit of a mess here because these prints are happening asynchronously, right? PDG is fundamentally asynchronous. So let me see if I can kind of pick out something here. It's really a bit of a mess. I'm going to try to run it again and see if we can get a slightly more clear output. Okay, so dirty all. And let's just try to run this again. And is that better? Slightly. Okay, it's good enough for me to point out what I need to. Okay, so the onGenerate in the clone is called. What you should notice is that the parents, only one parent is being passed in, okay, as opposed to all 3 parents being passed in all 3 work items from upstream being passed in the previous example, right? Because this guy only gets generated when he is actually complete. This work item is complete. Python processor 2 gets the onGenerate callback, and that list would only have a single work item, which is the parent who just completed, that guy, right? And likewise for this one, and likewise for that one. And therefore, if you look at these lists, they would only really contain one item as opposed to the 3 that we saw before. Okay, so that's it on static versus dynamic graphs. Next, let's take a look at partitioners. We can see that kind of by stacking the processors together one after another, we get fan-out behavior. But that is not going to be ultimately very interesting if we can't fan stuff back in. And that's exactly what partitioners do. It's you can think of a partitioner as a bucket that is able to take any number of things from one branch or from multiple branches. It grabs them and it puts them into a single bucket like this. And with that stuff in that bucket, you can go on generate off of the partition to create yet more work items. So not only does it do that, kind of bucketizing and grabbing chunks that of generated data from the work items, but it also provides synchronization. So you can be guaranteed that everything that needs to go into that bucket or partition is actually finished and computed before the partition itself is marked as finished, so that the generate downstream off of the partition will only be called once partition is actually complete, and thus everything that it needs is actually guaranteed to be there. The partition itself is also a work item, but it's just a special one that we mark visually with rectangles as opposed to these rounded regular work items. Okay, so that's basically the theory of partitioner. Let's take a look at that in practice. So I have this little graph here where 1 becomes 3, and we get 27 work items at the bottom. So I will use a partition by index. The only difference between all these different partitioners is just the mechanism by which they bucketize stuff. You can do it by index, you can do it by frame, you can do it by expression, and you can write your own. You can do it by any number of means. For simplicity, I will use the partition by index. And once I hook this up, when I cook it, it will create one bucket for every unique index. And because there are 27 unique indices here, it will create 27 buckets, right? And one for each corresponding index, as you can see here. So that's sort of the simple one. And just to show that you can combine from multiple branches of the graph, we'll have another generic generator here. And let's say put 10 work items here. And once we cook this, you'll see that it's picking out ones of the corresponding matching index based on both branches, right? And of course, you can have more work that gets generated downstream based on what is in the buckets, right? And does so for one for every single bucket here, right? So that's kind of the relatively simple case of it. Where partitioners get a little more complicated is if we have dynamic graphs involved, right? So here, remember this graph here, the second node, we started making this graph dynamic. So just to illustrate the concept, I'm going to add another node here, just to make it branch out a little bit more. Let's set the iteration count to not 5, but 2. And if I cook this, we should have 6 things here, right? So each one of these has 2 children, right? So now if I put down the same partition by index, let's see what happens, okay? So if I cook this, you'll see actually I don't have 6 partitions as you might have expected. I actually have 3. And if I click on this, you'll see that it kind of extends all the way up to the top. And so what's actually happening, and you can see this a little bit more clearly if I dirty this, is that the partitioning is is with respect to the very first static work items it was able to find, right? So here, you can see as I click on each one of these partitions, the corresponding sort of work item it's partitioning against is lighting up. And so what this is saying is I want to grab everything that you end up generating dynamically. So I'm going to partition, when I cook this, everything that this guy ended up generating, the leaves, okay, that it ended up generating will go into each bucket. So each bucket would contain 2 things, the leaves of the static work item it was partitioning against, okay? So you might say, well, what if I actually want to partition against this level, right, as opposed to the very top of it? This is when you need the setting called use dynamic partitioning, because these work items are dynamically generated. In order to partition against them, you would have to turn this on, okay? So once I do turn this on, and I dirty, let's just run this whole thing again. Now I get 6 partitions. Now they're partitioning against the leaf work items, right? In fact, you can choose kind of which level you're partitioning against by setting the partition target. So when dynamic partitioning goes on, typically we'll just go against this one, but you can give it some other node in this chain to partition against. So one last bit to point out, once a graph becomes dynamic like this, right? Starting with this node, it became dynamic. It stays dynamic at least until the point of where it hits a partitioner, okay? And the partitioner has to itself be static in order to stop the dynamicness of the graph. Okay, so here, to see this, I'm going to turn off the dynamic partitioning. I'm going to hook the generic generator downstream. And let's say we have it generate, independently 5 work items. I'm going to dirty everything and generate. And, oh, right. This is set to automatic. We'll have to say explicitly to static. Dirty all. Generate. There we go. For each of the partitions, it generated 5 work items, but it was able to do so statically without knowing what the dynamic stuff would actually end up producing. Okay, so that's one little caveat. Keep in mind that once you set the graph to dynamic, it basically stays that way, with the exception of what I mentioned here. So by now we've covered processors and partitioners. And in fact, these 2 constructs were all that you saw in the entirety of the launch video. Even complicated looking nodes, like for example the merge or the split. These are all just combinations of either processors and or partitioners. The merge is literally just a processor. If you double click, there's nothing else inside. So for example, we can see this working if I create some attribute called foo here. And let's say we just cook this. We'll probably end up just getting 1. But that's fine. And if I now cook this, we should have 16 things and not 15, right? So it literally just clones the upstream work items. So every other one basically clones from the left, but this one here cloned from the right. And if I had more things here, it would clone as well. So the merge is literally a processor. The split, if we bring up the help for it, I just want to show the easy way of kind of getting to some of these samples. We'll have these help cards. So we load that into the session. So if we look at the split sample here, cook that. If I double click on this node, you'll see inside that is actually made up of a bunch of other processors. So here is a attribute create processor, and then the filter by expression, which are in turn processors, and it goes to one branch or the other. And so it basically clones on one side or the other. Some of these nodes are assets like this, but at the end of the day, when you dive in, it's just going to be some combination of processors, partitioners, and mappers, which we'll talk about next. So basically with processors and partitioners, we have a situation where the graph can just kind of fan out and fan back in, fan out, fan back in, and it can do so endlessly. And with that, with those 2 constructs, basically we can represent anything, any kind of procedural process indefinitely. Okay, but you might ask, well, isn't everything procedural? And the answer is actually no. It's not always procedural because there are people involved. Where people, where humans enter the process, essentially proceduralism breaks down. So to see this, here is a very simple example. Let's say we utilize some of this wedge functionality in PDG to wedge out a ton of these Jersey barriers, okay? And we can describe that process procedurally. But then let's say we want to actually inspect the whole pile of Jersey barriers that we've wedged out, and we want to pick out some subset for further processing. Let's say, I don't know, maybe we want to put it in some kind of pamphlet, and we only want to pick out the ones we actually like, okay? That picking out process is a manual one. There is no information in the generation of the Jersey barrier that is going to allow some algorithm to tell which Jersey barriers the user is going to end up picking out, right? That information simply is not there. It's in the head of the user who is doing that picking. And so this process here is not at all procedural. I might select, this one on the left and this one on the right. Somebody else might choose, these 2. Who knows? So to actually model this, we have the idea of mappers. And what mappers do is join together 2 procedural chains. Okay, it takes two of these procedural chains and then it glues them together. So in this case here, the first procedural chain would be the generation of these Jersey barriers. And then there's some picking process, manual picking process. And then based on that selection, there would be a second chain of procedural that, let's say, takes the selected Jersey barriers and then generates a pamphlet based on the ones I'm choosing. Okay, so this actually brings up an important point because there's a long-standing problem in production where people don't really know how to properly combine proceduralism with non-procedural techniques like manual editing. Very typically, let's say we generate a procedural building and then somebody goes and does some bit of modifications on top of that procedural building. And then now we go back and change the parameters on the procedural building. And all of a sudden, their manual edits are blown away or no longer valid. So it's a long-standing problem that hasn't been well solved. The best people are doing these days are basically kind of selecting the stuff and then saying, okay, I'm actually, I don't want anything to happen here anymore. I'm going to freeze it. But the problem with freezing it is also that, you lose the benefits of proceduralism, right? You can no longer go back up and make edits to that procedural building. So mappers, by being able to neatly combine together two chains of proceduralism, could offer a good framework to actually solve this problem properly. To make things a little more practical and concrete, we're going to showcase the use of mappers to solve a problem that similar to what I was describing. So here in front of me is a beautifully generated procedural building. That is this box. And I'm going to go inside and I'm going to now apply a manual edit to this box by grabbing this vertex and moving it. So I have now an edited building. Now I'm going to simulate the idea of regenerating the original building, the procedural building, by changing the parameters of the original box. And you're going to see that this becomes an instant mess, okay? The manual edits that I've applied is just a total mess. And it's a total mess because of the fact that the edit node chooses to remember the point number of the point I choose to edit, right? And that was point number 7. But of course, once I change the topology of the box, point 7 is no longer the one on the corner, which I actually intended. So if you actually watched the Houdini 75 launch, we had the pleasure of having Mr. Bill Poulsen on stage with us. And he said something. He said that, if you looked carefully, the power of PDG comes from the fact that these operations that it performs are independent of the shape of the data. And so here is an example, a counterexample, where an operation like the edit was actually dependent on the shape of the underlying data. It stored the edit on point number 7, which, once the shape of the data changed, my operation no longer really was the one that I was intending, right? So let's see how we can use mappers and PDG to fix this particular problem and get topology-independent editing. Okay, so to do that, let's get rid of this edit, which we no longer need. Put our box back to its original state. And let's go to tops now. Down top network. Dive inside. And the first node we'll put down is this geometry import node. Okay. And we're going to point this thing at geo, that's fine. No, geometry import, yeah. And where do I want to point this? To a SOP node. And I'm going to point it to the box. And if I cook, that's importing details. I don't want that. I want points. Okay, I want to get all my 8 points of the box. And there we go. We have it. Okay. So there's my SOP path, point offset, and the numbers, the actual coordinates on each point. So the first thing we'll do is simulate the moving of the editing of the box by putting down a Python script node. I'll wire that up. And in this Python script node, which you notice is actually evaluating in process, we can grab the box geometry and make some edit to it. Okay, so I'm going to write a bit of code. So we're going to say, let's get rid of all this stuff. Here, okay, get rid of that. So import who, SOP path is stir data of the work item, which you saw from that comment earlier is one of the pre-built parameters. SOP path. Okay, and why SOP path? Because each one of these things has that attribute there. So, and point offset is int data and work item and point offset that. Okay, and let's get the SOP node next. Who.node the SOP path. Like so. And the geo is, let's get our hands on the geo. The SOP node, geometry, and freeze. We want it frozen so that we can actually make edits to it. If you just get SOP node geometry and try to make some edits, it'll tell you that it's read only. So, and we want to get ourselves the point, geo.point and pt offset. Let's just save our file right now and just give it a test here to make sure it's all working. So let's call this test mapper. And just going to give that a quick cook, just to make sure it doesn't do anything yet, but just make sure the code is, well, made a syntax error. That looks good. And let's go on and let's get the position of that point. Position. And let's make a modification on that point position. Set position with position, I think it expects a tuple, position dot x, and we're just going to say arbitrarily add 0.5 on that, and position point y, and positions z, dot z. Okay, and close off my tuple and my call. And again, save, just going to quickly dirty and cook, just make sure I haven't made a syntax error. Looks good. So we've read off the position, we added 0.5 to the x coordinate, and now let's save out this geometry. Save to file. By the way, none of this is magic. You can just get all these methods off the Hom cookbook. Let's call this, I don't know, test mapper. Stir of the point offset. And of course, it's BGO. Okay, so let's save that. And dirty and cook. That seemed to have worked well. Let's go take a look at our test directory, and sure enough, we have all these BGOs. And if I sort of open up one of them, we should see that, in fact, yeah, so we're just taking the x coordinate and added a little bit to it. Okay, so that all looks like it's working. So I just want to make a quick point about the use of Python script nodes running in process like this. So be careful with it because what's not supported in it is like trying to modify the current scene. So you can see with what I'm doing, I'm not actually modifying the current hip file. I'm reading from the current hip file, but then I'm just writing stuff to elsewhere. I'm not really modifying it. And the reason that's important is because these work items a lot of times are being actually run on the farm. And if you think about how that actually happens, it basically has to take your hip file, your current hip file, it has to make a copy of that. It has to copy that onto the farm where it can actually be run in a separate process, right? And so if the Python script node is making change to the current hip file, well, you might have succeeded in modifying this copy of the hip file, but the ones that are running on the farm, they wouldn't reflect that change, right? So that sort of thing, the modifying the current hip file through a Python script node is not something that's supported. If you want to build up some kind of hip file and then use that, the right way to do that is through the Houdini server node. This one here, the Houdini server begin, and with a command chain to build up a hip file that way. One more thing, in addition to the restrictions on the Python script node that we just talked about, there's another one. You should be very careful about using the module who with the Python script node in process. The reason is threat safety. Who is not threat safe, and PDG, the way it evaluates, everything is completely asynchronous. So when the Python script node is running in process, it's running in some background thread, and that can cause problems if you're using who. So imagine, for example, our topnet was embedded in the middle of a SOP chain. We're running this Python script node while the SOP network is cooking. And we're using who to access some SOP functionality. So that could clearly cause a lot of problems. The only reason that I'm using it here is because, well, firstly, there's just no real quick way that I can really show you how mappers work without doing something like this. And secondly, in this case, it's okay because I happen to know that SOP network, that box, is not something that is actually cooking at the moment, and I'm just only reading from it. So now what we're going to want to do is simulate the picking of a point, and we're going to want to do that in a way that is, remember, independent of the shape of the underlying data. And so we're going to do it through this Python processor here. And what we'll want to do is here, simply get rid of the numlock. Go. We're going to do this item is item holder dot add WorkItem. Okay, and we'll set some basic attributes on this thing. Set float array. Call this bounds min, and let's say 0.3, 0.3, 0.3, and that's not a tuple. It's expecting it's an array. Okay, and close that off. And once again for bounds max, but let's say 0.7, 0.7, 0.7. Okay, so you have a minimum bounds and maximum bounds, and we have created a single work item like that. Okay, and in fact that is there. Okay, and once again there's no magic. If you want to see these methods, you can get it added the way I showed you by looking up the PDG module. In this case, these APIs are on the work item data. Okay, and you can look that up. Okay, so now that we have the work item here that represents the actual selection operation, it's time to write the mapper. Okay, and we will write a custom Python mapper to illustrate this. So let's name everything properly first. Let's call this import points, and this will be map points by bounds. This here will be select points by bounds. And the last one, let's call this move point. Okay. So we can see the structure of this thing now. So above the mapper is the first chain of procedural, where we generate our beautiful procedural building and we import its points. Below the mapper, we have these manual operations that are being modeled by this node here. The user is picking some point in the viewport, and we're modeling that through the bounds min and bounds max, right? And we're representing that edit operation in a way that is independent of the shape of the underlying data. Then a second chain of procedural ensues, where we take the points that we map to, and we're going to move those points and save the geometry, right? So you can think of some kind of manual edit as kind of a degenerate case of a second chain of procedural, right? A manual edit is a second chain of procedural with a single operation. Okay, so with that out of the way, let's write our mapper. So you can see here downstream item, upstream items are already defined. And so we can use that in our code. And so here, what we'll do is we're going to say for up item in upstream items, for down item in downstream items. We want to get the bounds min, okay, that is present in the downstream work item, right? The bounds min. And so we want to say bounds min is down item dot data dot float data array. And what's the name of that? That would be bounds min. And we want to do the same thing for bounds max. And let me just cook everything here and just make sure there hasn't been any syntax error. Okay, so we'll do that. And next, let's retrieve the actual from the upstream point. The actual coordinates of point x is float data up item. What's the attribute we want? We want p, and we want the first one, right? So let's replicate that a few times. 0, 1, 2, x, y, z. And one more time, let's just make sure that no syntax errors. That looks good. Okay, so now we're going to want to see if the x coordinate point x is greater than bounds min. So the first one, and up point x is strictly less than bounds max. The first thing there. Let's just say that for now. Let's just make sure there's no error before we go any further. Dirty and cook, that looks good. Okay, but that's not what we actually want to say. We want to say and. Okay, let's just copy this. Two times, so x, y, z, 0, 1, 2, x, y, z, 0, 1, 2, and I don't think we need that last, and okay, so close the paren, and just make sure that's all good. And cook, yep, that's good. Okay, we don't want to actually do nothing, so we want to say if this is true, then dependency holder dot add So it's right here actually, dependency holder dot add dependency, right? Add dependency. I don't want two dots here. One of them, and call that down item and up item. Okay, so that should already establish a dependency for us. So sturdy and cook. And did that work? Yay, that worked. Okay, so 0.3 bounds at 0.3 to 0.7. And if we look at the coordinates of this point, it's all 0.5. So that is the only one that matched that description and only one where we have this dependency established. Yay. All right. Now, in order for the points down here to actually get moved, you see it's actually expecting these attributes. So we better kind of copy that on there. So let's do that. So down item dot data. Just move here a little bit so we can see what we're doing. Down item dot data dot set float p, right, and up point x 0. And let's just make sure we have that. Let's cook that again. And do we have that? Good, at least one coordinate. So let's get the other ones. X, Y, Z, 0, 1, 2. All right. And let's cook. And cool, that's there. All right, now we better get the other one, the SOP path, right? That's down item dot data dot set string. SOP path. And what's the value? It's stir data, up item, SOP path. Close that off, and 0. There we go. And let's see if we did that properly. Dirty and cook. Cool. That seemed to have worked. SOP path. That's good. That's there. And one more. And I think we just need the point offset attribute. So in the future, we might make this a little bit easier, by sort of maybe automatically doing this for you, inheriting the upstream items data. But for now, it's a bit manual. So we'll say point offset and int data up item. And what's the attribute name? Point, same one, point offset. And close paren, 0. And let's see if that worked. Dirty and cook. And now we have the point offset. Excellent. All right, now if we cook our move points, we should have our BGO dumped out. And if we look at the timestamp, 529, that should be, oh no, wait, 556, that's the one, okay. And does that look valid? Yes, it does, right? Cool. Now, moment of truth. If we now go back up, right, and now change the topology of the box, hopefully we will have our edit operation still something that that is valid. Okay. So here I'm going to simulate the re-importing of that of the box by dirtying this node, but notice it didn't destroy our manual edits. That's still there, still valid. So if I just cook this again, and now lo and behold, we have 26 points because we've upped the tessellation. And hopefully now, if we look at the at our modified BGO here, with a timestamp of 557, look at that, right? That is still the point I wanted to move, right? Even though the topology has totally changed. Okay, so the sample might still feel a little bit contrived in the sense that we sort of hard-coded the selection operation right here in this processor. So what I've got in front of me is a almost the same file, but slightly different in that I've added something now to kind of mock up something a little more realistic. Okay, so you'll notice that on this box here, I have this button called Select Geo. And what this thing does is it utilizes some of the APIs we have to allow actually the injection of work items. So what's going to happen is that as users are working interactively in the scene, as they perform certain operations, you're able to call these APIs to inject the work items into the right spot and cook the graph. Okay, so in this case, I'm going to click this. I'm going to select this point, press enter. Do it again, maybe with this point, and click enter. Now, if I go back to my topnet, all of a sudden you realize that actually there are 3 work items. There are 2 more that have been added via this mechanism I'm describing. And if I look on disk, and I should see some pretty newly modified work items, right? Baked out BGOs from those 2 work items that I just injected. And if I kind of take a quick look at them, let's bring that up now. Took a little bit, but there it is. Okay, so that's one of the corners I selected. And here is the other one, right? So there it is. Okay, so let's take a quick look at how this script actually works. So if I bring up my Python source editor here, you'll see it just invokes some standard HOM stuff to allow me to select the geometry. Then once I selected, figured out what's selected, I parse it out, the points that were actually being selected. And based on that point, I calculate some bounds min and bounds max like we have done. And then here's the critical call. Once I have the PDG node, I can say inject static items as holder. And then this allows me to get the work items in there. And then I can trigger a graph cook like so. Okay, this is the Python version of this functionality. There also exists Houdini engine equivalents of this functionality. So you can inject work items as needed as the user is working interactively. Okay, to sum up, mappers tie together 2 chunks of proceduralism. Here is the first chunk of proceduralism. Here is the second chunk of proceduralism. Here is a description of the manual operation that one wants to perform. And the mapper ties these 2 chunks together by allowing the manual operation to kind of pick out the bits of the results of the first chunk of procedural using its attributes, right? And it does so in a way that is independent of the shape of the underlying data. And so it's going to work even if the first chunk of procedural stuff gets regenerated. And that's it for mappers. All right, next topic is customization. So once you've created your custom functionality with Python processors and mappers and partitioners and whatnot, you might want to create your own custom node and have a proper interface around that. And we provide 2 ways of doing it, each with its pros and cons. So you'll notice on the left here, I've highlighted these 2 buttons here. One says save to Python script, and the other one save to digital asset. The one on the right, save to digital asset, is the easiest flow. The advantage is that the code remains editable through the HDA, but the downside is that it can't be called from sort of pure PDG. You can only use it within TOPS. By pure PDG, I mean like a pure Python implementation of the node. And so if you want to use it like outside the context of TOPS, using just Python, then you need this. Okay. The other mechanism, the save to Python script method, allows you to do that, allows you to call that functionality through pure Python as well as TOPS. But the downside is that the code is not editable through the HDA. So let's take a quick look at this in action. So I've got this previous test file that we saved out. loaded up. You might remember we have this Python processor here that, printed this just on generate called with parents thing. Let's try to just save that out. Let's call this, generate with print. Okay. And I might say, save the digital asset. And let's call this that, generate with print. And in 17.5 OTL, say accept. That's done. And if I now tab, it's right there. Okay, so if I just get rid of this guy or disconnect him and tab, generate with print, hook that up. And if I cook this, did it actually print? There it is. Okay, so let me just clear this just to be clear that it actually did print that. There it is. Okay, so same functionality, and with the HDA, of course, you can now go and customize the interface on this thing, right? And just to show also the code, if I go to type properties and scripts, you'll see that all the generated Python code is here, and you can just edit that right here, and it will work. So just to quickly illustrate the other one as well. So if I just click this Python, save as Python script, notice it's the place where it's saving it, PDG types. That's where it's going to look for all these Python scripts that you save out this way. The system will automatically load it up. So, and let's call this something else. Generate print pi. Generate with print pi, just so we can distinguish that. Hit accept. And if I tab again, there's my other version of this thing, right? And I kind of hook it up. I'm just going to cook it. There we go. Clear, just dirty and cook. There we go. So it works the same, okay? And lastly, I suppose if we kind of go look in the right folder here, documents, DD17.5, PDG types, here's that Python file, and if I bring up the text editor on this, you can see that it created some of the boilerplate code for us, and the actual important code is here. Okay, so those are the two ways to do customization. Before we break, I'm just going to quickly touch on this topic of schedulers. This is a big topic that is deserving of its own masterclass. I'm going to talk about the very high levels of this thing here. Okay, so now the way the PDG works is that at any time it knows there's a pool of work items that are kind of ready to go. And it goes through the scheduler interface to say, hey, Mr. Tractor, Mr. Deadline, whoever it is, I have this work item I need to get done. Would you do it for me? And the work item gets serialized, the attributes get serialized to this JSON file. JSON file gets copied to the right place on the farm. And then the scheduler does its thing. It invokes the right application, for example, Houdini, Maya, or Arnode, what have you, to actually compute the work item and produce the actual right results, right? And it comes back, and that scheduler interface is responsible for informing PDG that, hey, this work item is actually completed successfully. So here is where you would also enforce certain facility policies at the scheduler interface layer. So for example, not wanting a single artist to take up too much farm resources. So no matter how much work PDG is throwing at it, here's when you say, sorry, Joe, I know you got 200 jobs to go, but you're only allowed 5 blades on the farm, okay? So that's pretty much it for the 10,000-foot view, but I'll talk a little bit about the specifics of one such scheduler, the local scheduler. This is the one that sort of is inside every single topnet by default. And what it does is just utilize your all the cores on your machine okay, and treats the local machine as kind of a mini farm. So you'll notice first thing here, the maximum CPU to use is by default set to 1/4 of the total CPU count. This is so that we don't oversubscribe your system. When we had the default to be something like this, some users ran into trouble because they were spawning these massive number of jobs, and each job was using GPU memory. And so the system became unstable because the GPU memory became exhausted. So you can crank out more performance out of your PC, but just keep in mind that what are you asking your machine to do? If it's too much, you can actually get it to crash. Okay. HDA processor pooling is a feature where you can actually, if you're computing HDAs, use this feature to keep a number of these HDA processors in memory and spun up and warm without tearing it down, almost like a service. And so you don't end up paying the spin up and shut down cost of spinning the HDA processors up. Okay. The job params tab has this thing called single. If you have something that is already using a lot of threading, you might not want too many of those to run on the machine at once. So if you take this off, only one instance will be able to run. And by choosing CPUs per task, you can kind of customize exactly how many jobs are running on your machine at one time. So if I were to set maximum CPUs to use to all CPUs, let's say, and if I had 20, for example, then if I set CPUs per task to say 4, then 20 divided by 4 is I just get 5 things running at the same time. And you can control how many threads each job is using if that job happens to be a Houdini-related thing by setting the Houdini max threads count. The task environment thing is important for some things. Like if you want to run a different version of Python, for example, you would want to set the Python home and Python path variables. Typically, I would clear out Python path and set Python home to something like this. If I have Python 3.6 installed on my system, it would be like this. It's wherever the Python executable is actually living. Okay, so just as a quick test, I'm going to put down Python script node and get it to print out the version, right? So by default, it's evaluating in process. So if I say, import sys and print sys.version, and if I cook this guy, we should see if I get my console up, there we go, 2.75, right? So that's the default Python. Notice, though, the task info here, there's no log, right? Because this is running in process, right? So it shows up in the output console, right? So if I were to try to run Python 3.6, it would be not evaluating in process. I don't want Python, I want custom Python. And the path happens to be where I installed Python 3.6, right here, python.exe. And if I now run this will cook fine. And if I look at the task info, show the log, Python 3.6. Okay, so that's about it for this topic. Okay, so we've covered a lot of ground today, and we're going to break. Just before I do, just a couple of common pitfalls and tips working with PDG. So firstly, look out for single output files. So PDG is a templated processing graph. There can be many instances of a node running. So if you have a single output file that's independent of the sort of the instance number, then all these instances will write to the same file, which is most oftentimes not good. So if you see something like that, that should be kind of a orange or red flag. Okay. If you didn't save the file, remember the way PDG works is that it would save the HIP file and it would copy the HIP file to the locations on the farm where it would get run. So if you don't save the file, those changes will not be reflected, right? So a lot of times we prompt you to do this, but just make sure your file is saved. Next point, order of the parameter setting on HDAs is not guaranteed. So if you have an HDA processor, we will dutifully set the parameters you specify, but the order is not guaranteed. So, for example, if one of these parameters can have some kind of callback script on it that can impact other parameters, then that can really mess things up. So one example is the side effects spaceship. It has a randomized parameter where if I touch it, it'll go and set all the other parameters. So we had a problem at one time where we set some of the other parameters like the ship length, the wing aim, and then because the random parameter was set later, it destroyed all those earlier settings, right? This one we already talked about. And lastly, when you work with schedulers, some very common issues are, UNC paths, not having the right permissions to write to a particular folder, firewall issues. Just keep an eye out for those things. And lastly, just a quick reminder to not use the Python script node in process with the who module, or at least be very, very careful with it if you do because of threading issues. So that's about it. It's a long one, but thank you for listening.